All right, so.
Can we get quiet
Hey,
on
there.
some respect for Spain,
Hey there.
guys? Come on.
Hey there, chat. All right, no, we are going to continue talking about the math that goes with Newton's laws, specifically highlighting Newton's second law because, as we stated previously, it has Newton's first law built in it. You will see that a ton today. So, to remind ourselves of yesterday, the last thing that we did was we had Aiden in a chair, okay, and he needs arms. There we go. Okay. Remind me real quick of a few things. Let's talk force diagram real quick. What was this force diagram?
Force gravity down.
Gravity down. Force normal up.
Was he moving in this chair?
You saw the situation yesterday. It's
Friction
exactly
backwards.
the same. Yes. It's
And
be
then
friction
force,
backwards.
Not compression, but T.
Tension. Correct. Forward. And remind me of numbers real quick. What was his mass?
72 kilograms.
Next.
Took him 17. It took 17 newtons to get it.
Let's do this. What was our final answer yesterday? How much was friction? There's technically two answers. How much was friction that we calculated at the very end of yesterday?
10 pounds.
10 pounds is one answer. I would like it in newtons, and that's not to be a but. I'll explain why later. 44.5 newtons. Yeah. So force friction that we figured out was 44.5 newtons. And what was, had you write this down yesterday, we didn't use it yet, what was the maximum force when he was getting going that I told you?
Oh, yeah, I remember. 17.
Can confirm?
Yes.
17? Cool. So, let's look at this situation again. Actually, I'll write that down in just a second. 17 pounds. Okay, but let's review the math that we did yesterday. And I admit again, that to do this math, it's a little silly right now. It's gonna say stuff that you pretty much already know. What do we know about the size of force normal compared to force gravity?
The same.
100% it's equal. And what do we know about tension compared to friction?
Probably
Also
the same.
equal because they are balanced and the acceleration is zero. It's super simple, but it will stop being today. So let's make sure and practice this again. Here we are. Here's where we began. Specifically, I'll talk about the X. I know we did the Y as well. This is how you begin all of these problems. If you get confused, write down this next series of steps. Now, ultimately, it's just Jafeeps, like we've talked about from the beginning, with maybe a couple things in there as well. Given and find. Boom, there's me writing my numbers on the side. Unfortunately, unlike two-dimensional projectile motion, I can't make a chart because I can't tell you ahead of time what everything is going to be in the problem ahead of time. So we kind of just have to look at it as it stands. We'll do that in just a minute. In this particular case, I think we were finding friction, but we already have that. We'll show that in a second. The other part of the given that is necessary on every single one of these problems is a force diagram. 110% necessary. I'm putting points on it. You skip it. A, you're shooting yourself in the foot for solving the problem, but B, I will have points associated with force diagrams on every problem, even if it is not directly said. Okay, so next is equation. For equation, after you've done the given, you've done the force diagram, you wrote down your find, the equation practically starts the exact same every time. It is Newton's second law. And what is Newton's second law?
F sigma equals
Yeah,
F
sigma
A.
F equals MA.
Yes, the sum of forces is equal to mass times acceleration. In just a second, at the end of this problem, we'll talk a little bit more about that sigma part of things. But yes, there it is. And more specifically, as you can see me doing right here, we usually do it in just the X and just the Y, because similar to projectile motion, the X and the Y can run independent of one another. So here's how I start. I start sum of forces equals mass times acceleration in the X. I always start with Newton's second law, even if I know it's first. And the way I prove it's first is this very first thing. Is he accelerating in the X when he was at constant velocity? No, which means acceleration is? Zero, which means this cancels out, and that immediately puts us in Newton's first law. I could rewrite it right now. I did this yesterday. I'm not going to make you rewrite it every time, so I'll just say it. That now says sum of forces on the X is equal to 0, or they are balanced in the X. Now the next question I said was, what is the sum of forces in the X? Not 0, but what are they individually? This is that thing we did yesterday where I said, hey, is the force in the x? Which direction is in the x? Is it only in the x? And we got force tension minus force friction equals 0. And very, very simplistically, we found what we knew ahead of time. Force tension equals force friction, and that's where we got our 44.5 newtons. We knew that tension was 44.5 newtons because we measured it, and therefore friction also has to be 44.5 newtons. Everybody cool so far?
Yeah.
All right, let's go to an example I've used a couple times because I really want to make sure that you understand it. All right, I've talked about 1 kilogram. I've talked about the definition of a newton. The definition of a newton is imagine Spanauer in space. Now, why do I keep saying that? Why do I keep saying imagine Spanauer in space at the beginning of the example?
Because everything's equal in space. Everything's at an equilibrium.
If I let this go, obviously here it would happen. If I was in space and I let this go, what would the forces be on this?
Nothing.
Nothing. So the reason why I highlight in space is that the only force acting on it in that case would be me. Yes? So 1 newton is defined as however much push it takes to accelerate it at 1 meter per second squared. That is 1 newton. That's why if I let this go on Earth now, okay, it's 1 kilogram, how much will it accelerate? 9.8 meters per second squared, which is why that force is
not round.
no. How much? How much force is on this?
Oh no.
Because at 1 kilogram,
Or it's one
Except-
9.8 newtons.
9.8 newtons, aka that's this object's weight.
Drop it.
Its weight, no, I put enough holes in this one. Okay, 1 kilogram accelerating at 9.8 meters per second squared is exactly 9.8 newtons. Meaning if we go back up to space, and instead of pushing it with 1 newton, I push it with 9.8 newtons, guess how much it's going to accelerate?
Same as good.
9.8 meters per second squared. That's what a newton is. Now, here's the important factor that I want to get into. I set that mass on the table. Does it still have a weight of 9.8 newtons?
Yes. Yeah.
100%. Is it accelerating?
No.
It's not accelerating at 9.8. So it's not its weight that decides its acceleration, right? What decides its acceleration is the net force on it. When I dropped it a second ago, there was only 1 force, so the net force was 9.8. Now, the net force is what?
0.
And therefore the acceleration is
Zero.
0. This is specifically highlighting the importance of that little guy right there. It is not one force that decides what the acceleration is, it's all of them. And that's kind of easier to see when it's just one force, gravity or me pushing, versus, yeah, they're balanced and so it's 0. So let's look at a slightly different situation. Let's imagine we go back up to space, and this time I'm going to push it with 5 newtons. Now, if just I push it, how much will it accelerate? I push it with 5 newtons, 1 kilogram, how much is it going to accelerate? 5 meters per second squared. But you don't like that fact that you're standing next to me. So you try to push back, okay? And you push back with 2 newtons. So does it accelerate at 5 or 2? Neither. What does it accelerate at?
3.
3. The net force between us is what decides the acceleration of this object. Does that make sense?
Yeah.
Let's look at one more circumstance that I think will help this out a little bit more. Imagine you will, we'll come back to that problem. I'm not done with it. Person standing on the ground, easy peasy. I'm not going to make you do the force diagram because it is so simple. It's just force gravity and force normal. Okay, here it is. Behold. Sorry, people online. I am standing, and I'm right here. Here we go. Now, I am now going to jump. Okay, so I'm jumping, people online. Okay, here we are. While I was in the process of jumping, how does that force diagram change?
Force normal goes more up as you go closer to the ground. More up.
I liked what you said to begin with until you ended. Okay, agreed. Force normal is more up until you get close to the ground. When are you thinking force normal is bigger?
So you're getting closer and closer to the ground.
I like this.
Bigger and bigger.
No. Hold up. Okay, I think I see where you're coming with. I'm trying to think of it. You have this as I'm pushing with the ground, right?
Yeah.
Obviously, once I get off the ground, what's my force diagram?
Force
Just
gravity.
Just force gravity, and it's back to just 1D kinematics, and everybody goes, "Yeah, we missed 1D kinematics. I saw the pain in your eyes in 1D kinematics. Don't let me forget that, okay?" He's like, "I want to go back." No, you'll be fine. All right, so here's the deal. Here's what I want you to see. Where is force, sum of forces in this situation? Well, here it is. This amount of force normal right here, just that right there, would balance out force of gravity by itself. So this extra bit
Gets you off
right
the
here, that is the sum of forces. That's what decides how much an object is going to accelerate. How are we doing?
Good, pretty good.
Cool beans.
Okay.
Let's go back here. What we're going to do with yesterday's example is we are now going to say, okay, let's look at Aiden, not when he was at constant velocity, but when he accelerated. What would be different about my force diagram?
They wouldn't be balanced.
And specifically, let's run through them at a time. Is his force gravity going to change?
Nope.
Nope, because his mass didn't change. Is force normal going to change?
Nope.
So I've got to push up the same amount. Here's an interesting one. Is friction going to be different?
Yes.
Not really.
What?
The pull of the ground back on him, it might be a little bit, but noticeably it's about the same. So actually this friction that we calculated in the last problem, we're going to assume that it's the exact same friction in this particular case. Okay, so what does change?
F tangent. Or not tangent. Sorry.
You're fine. We've used that one before.
Why
Force
tangent?
tension should be
Tension.
bigger. About how much bigger, guys?
Double.
Nope. There's a number.
1.5.
7, 10.
About 7 pounds. How do we do that?
Oh, you're so awesome.
No. You got this. What's that?
The constant was 10.
Yeah, we know that 10's pulling back, 17's pushing forward. Now we should probably have that in newtons. Now the question is, so if force tension is 17 pounds, okay, should we keep that in pounds? So someone convert it for me so we can tackle that later. But now what we're going to do is we're going to try to find the acceleration of Aiden in this particular case. So we've got our given, we've got our find, and our equation. Here's the cool thing. What I just put over there to start us off with is identical to exactly how we're going to start this particular setup with only a couple of quick changes. So what I'm going to do is I'm just going to use that exact same setup that I had just a second ago, and I'm going to switch to yellow here. Everything that is different about that setup, I'm going to put in yellow. Now for your sake, I would probably rewrite this. Okay, right, Oren?
Yep.
Cool beans. So how am I going to start? Well, which way is he going to accelerate? X or Y? X. So I'm still going to start summing the forces in the X just like I did before. I'm just going to ask the exact same questions I did at the beginning of yesterday. Number one, is he accelerating?
Yes.
Yes. So rather than cancel it like I did yesterday, just leave it alone. Number two, what are the sum of forces in the X? Well, are they actually any different?
No.
No. Now, technically one of them is different. What is it?
One of them's the max. When it's
Technically,
like
tension
velocity,
is different. It's a different number in there. That's why they're unbalanced. That's why they're not equal to zero here. So is tension equal to force friction?
No.
No. But from this point forward, it's a pretty darn easy algebraic problem. What do I need to do to get acceleration? Do algebra here. What do I do to get
Divide
A?
by M.
Divide by M. And if we want to find acceleration, humor me with this. Why was it ridiculously important? Why is it important that our units are in newtons and not pounds? What is a newton defined as?
Force. And then how are you going to divide?
No. The force of what? I go back to my space example. What is a newton defined as?
Force acting on an object.
The force necessary to do what?
To move.
To make 1 kilogram move at.
1 meter per second.
So if you want your acceleration in meters per second squared, and you want to use kilograms, what must be your force unit? Newtons. Technically, by the way, English units do have equivalents. Nobody ever uses them. Pounds are, of course, the unit for force. The mass that goes with that is known as a slug, although no one ever uses it. It's not even a slug directly related to like guns and that type of thing, if you're into that type of. And of course, acceleration would have been in feet per second squared in that particular case, but nobody uses it, so we have to be in newtons. Here's a simple thing. To use Newton's second law, you gotta be in newtons. So here we go. What's force tension? In newtons?
75.6.
75.65. Let's go 75.7 newtons. Minus, what did we say force friction was?
44.5.
And what's mass? So go ahead and calculate what's his acceleration. Anybody got it yet?
My couch is dead.
Feel free to work ahead. So are you, according to your ability to stay awake.
I'm sorry.
Yeah, all right, it happens. Just do best.
Don't
Don't feel bad when I yell at you. I'm not yelling at it, but yelling
Okay.
so much. General yawning. I can shoot darts at you if that's easy. What's that?
Stop
Okay, good. I'll get up and return.
yelling.
Don't fall asleep in my class. I'm volunteering for target practice. Mr. Sparrow, we're calling you into disciplinary action. Apparently you're saying you shoot kids with darts. I never said that. We literally have you recorded on a YouTube video. All right, now, let's do this real quick, because I know it's simple to calculate. You ended up with, what, 31.2 divided by that, about a half, right? A little less than a half, 0.4 meters per second squared.
0.43.
Fair enough, 0.43 meters per second squared. Does it make sense with what you saw Aiden do yesterday that he didn't accelerate super fast? About 0.43 makes sense with how you saw him speed up yesterday? Yeah, 110%. It should. Now, let's highlight this real quick. Somebody, you probably didn't do this individually, which is fine, but I want to show it real fast. It's this. Take 75.7 just minus 44.5. What do you get?
31.2.
31.2 newtons. What is that?
That's your sigma.
Correct. 31.2 is
How are you gonna do?
your net force. That is how much total force is acting on them, and that is why that's what's used here in this particular case. Because in the previous example, I could have technically done and not canceled acceleration, except in the previous example, when he was at a constant velocity, friction would have been 44.5, force tension also would have been 44.5, and 44.5 minus 44.5 would have given you 0. Doesn't matter what you divide by, the acceleration would still be 0, and that's exactly right. He did accelerate at 0 meters per second squared because he was at a constant velocity. How are we feeling? All right, let's give you guys a little bit step up in difficulty here. Please make sure that if you don't understand today, you are asking questions. This is the day. This is the day when it steps from like, seems easy to, oh crap, I got lost. And if you get lost, number one, obviously we've got the video here, but number two, please make sure and ask good questions to understand this a little bit better. All right, here's what we're gonna do. We're going to look at this problem right here. It's a lot of wording, but it's just the bottom half that you actually need, so I'll talk about it real fast, and then we'll get going. Prior to manned space flights, okay, so prior to shooting up into space, the rocket sleds were used to test aircraft, missile equipment, and physiological effects on human subjects at high speeds. You've probably seen meme videos of that guy that kind of basically traveled so fast that the desert his face kind of gets pulled back into black and white. Yeah, he was on a rocket sled in that particular case. They consist of a platform that's mounted to 2 rails, so they're using usually railings, and propelled by several rockets. Almost always it comes in 4s just to even out balance in the X and the Y. But have you seen a rocket sled? Do you know what I say when I say rocket sled, or does that seem kind of,
I know.
you know what, I got a video.
I'm watching enough Mythbusters.
I was going to say. So, if you've never seen a rocket sled, here is one in a nutshell. In this particular video, we're not going to watch the whole thing in case you got excited about that.
It's only 4 minutes.
Yep, we're not watching that. I don't have enough time. Okay, so a rocket sled, in this particular case, they were testing the myth. They had 2 semis crash together to see if you could fuse a small car in between 2 of them. They found out they did it for real. It was amazing. They found out, no, you can't, but they wanted to amp it up. So they amped it up. They went to a rocket sled so they could shoot off a rocket sled at about 700 miles an hour, I think they say. Well, let's show you the picture of it real quick here. I'm just going to flash. It's kind of hard to see here. I thought they had it.
Yeah.
3. Okay, so it's hard to see over there. Well, I'll show you the fast one first. This is what happens.
2, 1. Used to but when the second stage kicked in, I was thinking I've never seen anything go that fast. And then I realized actually that's correct. I have never seen anything go that fast. 3.
Awesome is such an overused word, but that truly inspired awe. And then some. Incredibly, the spectacle of the launch.
So I think I have to go to the end to show you a good picture of it.
Where's the slow mo a little bit to the right?
Yeah, they do a slow mo at some point here. Okay, here, I think it's right here. So you can see it. You can actually see what it looks like for a second.
For encore.
All right, so there it is. In this particular case, it is a giant piece of metal. They've got rockets on the back. If you watch this video, they actually do it in stages. They hit two, and then they hit the other to get even more acceleration. But there's a giant piece of metal right here. It was on rails. It's not important. Here we go. Now, what we're going to do is this problem right here. Okay, at the bottom. We're going to calculate the magnitude of force exerted by each rocket in the following situation. So thrust is typically what they use for rockets. It's really just electromagnetism, but we'll call it thrust, just capital T. Today, I'll just use a single T so we're not confusing it with force tension. This is important, 4 rocket propulsion, there are 4 rockets. Notice it's asking for the thrust. T is just 1 rocket, but there are 4 of them. Okay, the sled acceleration is going to be, make sure you're writing this stuff down. Come on, here we go. Acceleration is going to be 49 meters per second squared. The mass of the system is 2,100 kilograms. If it matters to you, that's about 5,400 pounds. By the way, acceleration 49 meters per second squared. Is that a lot of acceleration? That's 5 times how much gravity accelerates you. To put that in perspective, if you want to accelerate at 5 times gravity, your weight accelerates you at 1 gravity. So how much force is necessary to accelerate you?
5 times me.
Whatever your weight is, multiply it by 5, and that's how hard you got to get hit to accelerate at 5 times gravity. So the mass of the system is 2,100 kilograms. The force of friction opposing the motion will assume to be a constant 650 newtons. And the question is, what is T, the thrust of each individual rocket? So when you're dealing with a situation like this, okay, it is absolutely a thing that students regularly experience, to be kind of like, I don't know what to go. So always set up your puzzle with the outside pieces first, aka do what you know to do. Start with your given. What's one given?
Acceleration equals 49 meters per second squared.
Correct. Next.
M equals
2,100.
Cool. What's next?
Force friction equals 650.
Cool. What are we trying to find?
Force T.
T.
Would that be
Cool.
force T?
You've done the given and fine. You can do whatever. I'm just only going to put it as capital T to separate it from force tension today, because we're going to use force tension here in a minute. Next. What should we do next?
Drop T minus.
Specifically a
Force diagram.
If you're confused on these problems and haven't done a force diagram, I don't know what to do with you. If you are sitting there and like, I don't need a force diagram to do it, then you drew it in your head. Draw it for me. You are not doing these without drawing some type of force diagram, either in real life or in your head. So just put it down for me as well. So here we go. I got you a rocket. There are 4 rockets on here. There we go. It's on rails. Help me out. Force diagram, go. You know what? Let's go 30 seconds without me. See if you can't do it on your own.
Okay.
Got it.
All right, see what you got?
We're supposed to give the whole answer, or just draw the force?
No, just draw the force diagram. What do you got?
I'm good.
Down with force.
Nice.
Force T to the right.
Okay.
Force
We'll
normal
hold
up.
on a second with that. We'll wait on that in just a minute. Force normal up.
Friction.
Yes.
All right, now I'm going to draw what's wrong and see if you can't spot it.
Divided by 4.
Not
Nope.
quite.
No.
Not quite. T was defined by the problem as being
Wait, you need to take that line and make 1/4. Make it 1/4 as long.
not quite. Not quite. There were 4 rockets. Each one rocket said it was
So
giving
there's-
T.
Oh, you
So
did that.
you have 2 things that you can do here. Either one, I don't care which one, I really don't. Either one, you draw 4 T's, all the same direction, okay? And when you draw forces the same direction, you just kind of stack them. They don't have to draw them from the center. Just make sure they're going the same way. Okay, make sure you don't stack them on top of each other. Okay, or more, if they are going the same way, and only if they're going the same way, you could draw a single arrow, but how should you label it?
4T.
4T.
40.
Why is it 4T? Because technically, what have you done with those 4 arrows? You have done a vector addition with the 4 of them and stacked them on top of each other. Now, we've done a given and find. So what's next?
So the equation.
Which is?
Sigma F equals MA.
Correct, and specifically in the y and the x. Now, only go for what you need, but sometimes you don't know. Try something. Why is it probably not a great idea to sum the forces in the y here?
Because we ain't going up.
Sure. Also, what's it going to solve?
That's it.
Well, it's going to tell us force normal. But what could you tell me about force normal already? Probably the same as whatever force of gravity is. How do we calculate force gravity? What's its equation?
Fg equals mg.
Correct. Fg equals mg. So, not going to be helpful here. So, if we don't sum the forces in the y, we should probably sum the forces in the x. So, once again, I'm going to give you 30 seconds to try to fill out that, asking the questions that we should regularly ask. Is it accelerating in the x? Accelerating in the x? Yes. Next. What are the sum of forces in the x? Fill that out. Do a little bit of algebra. You should be able to solve this entirely on your own.
I'll try, just for you.
What throws me off is the sum of forces, but I think I'm gonna be able to get this one.
Okay, well, if you're thrown off by the sum of forces, keep in mind that you're just kind of doing a quick vector addition, and that is just as follows like we did yesterday. So I go around with every force and I ask the 3 questions I did yesterday.
Oh, wait.
Is it in the x? Which direction is it in the x? And is it only in the x? So, let's start with 4t. Is it in the x? Yes. Which direction? Positive, right? Positive x. Okay? Is it only in the x? So then I write positive 4t. Let's knock out these other ones real quick. Is force normal in the x? No, skip it. Force gravity in the x? No, skip it. Is force friction in the x?
Yes.
Positive or negative? Negative. And then is it only in the x?
Yeah.
So negative force friction. There's my sum of forces. And that has to be equal to mass times acceleration. Sure, max and may, if you will. Now, what are we trying to get in this equation? T. Cool. Let's use some basic algebraic principles. Do you know FF? Do you know M?
Yes.
Do you know A?
Yes.
So you only have one unknown. Basic algebra. Solve for T, get the answer. You got 30 seconds to get in front of me, then we'll get going.
Can I play sound ball again?
On your free time? Sure. Does it look like we have a ton of free time in here? My favorite thing that has ever happened, and I appreciate it's not happened in a few years because I think students have learned who I am, but like probably like for early part of my career, regularly I was asked, "Hey, Noah, can you watch a movie today?" And I laughed at them. It was embarrassing how hard, like it was embarrassing for them how hard I laughed at them. I didn't show you a 4-minute video today because I'm going to run out of time at the end of the hour. All right, what's the first thing I should do algebraically?
Shoot, I got lost. Divide by.
Nope.
Add.
Yep.
Minus 40.
Add.
Add F.
Now, this is an interesting point that I want to highlight here. Please notice that we have put the negative here for force friction already. When it comes to forces, and forces specifically, they are not ever negative in these problems. You don't have to force them to be negative. We are already taking care of the negative here. So I'm going to add that on both sides. And then simply I am going to divide by 4. Thank you. Yes. So I've got this set up. Let's go ahead and plug in. What's mass?
It's 2100
2100 what?
kilograms.
Always, always, always units, even when you talk. What's acceleration?
49 meters per second squared.
Correct. Real quick, if I stopped right here, somebody do this in your calculator. What's 2100 times 49?
102,900.
So like in the 100,000s. So does the 650 newtons probably do jack squat to this answer? Not very much at all, but we'll add it in anyway.
A little bit of thrust.
And divide by 4. What'd you get?
I got 25,562.5.
All right, I want to address that real quick here because I think all of you guys do this. If you've got a big number, I know you want to write all the numbers. Why? Here's a simple thing. Write 3 significant figures, round appropriately, write the rest of them zeros so you don't have to spend a bunch of time tracking stuff that really doesn't matter. Now I know it feels bad because you said 2,500 what?
25,562.5.
562, so
it was really
can confirm, by the way, I got a slightly different answer last hour.
I got 25.
887.
Yeah, I think
That's all I got.
that is right. 25,001?
887.
887. So I'm rounding this to 900. And I know it feels a little bit weird, but does 13 do jack squat when you're talking about 25,000 of something? Like if you had $25,000 in the bank, are you gonna stress that much about losing 13?
You know what they say? Hey, experts stay rich.
Moving on. All right. So there is the thrust of an individual rocket moving forward. I forgot to do something on the last problem I wanted to highlight real quick. It's not going to take me long. Let's go back to this real quick here. Let me ask you this with the Aiden problem back here. What would happen? So Aiden's going along. Okay, we accelerated him, blah, blah, blah. He was right at constant velocity. What technically happens to Aiden in this force diagram if I stop pulling? What happens to the force diagram?
There's no FT.
Correct.
So FF slowly slows him down.
So that would just be this. That would just be this. That would just be this. Does it make sense that Aiden would then get a negative acceleration from being unbalanced? Because he should slow down, and you could easily calculate how much. Moving on. All right. 2 more examples for the day. This next example comes straight off of your homework, the same assignment that I did yesterday. It's 4.3. Yesterday, I think we did number 8, or 2 days ago. Number 8. Okay. Today, we're gonna jump down a little bit because number 9 is exactly the same, and we're gonna look at number 11. Because I noticed that a couple things in the past. Number 1, number 11 is a little bit hard to kind of understand what it is they're trying to do, and number 2. We have only dealt with examples so far that have forces nicely in the X and the Y, and they're just right, left, right, up, down, and that's not realistic for what actually happens in life. So we need to look at situations in which the force is not so nice in that direction. Now the question here, it says you got a 200 Newton mass hanging on a boom that's attached to a wall, 30 degrees. But I know from previous experience and having done this myself, this is hard to visualize what's actually going on. So let's do this.
What? He has it.
Have it ready to go. Here we go. What's up?
Yeah.
Hold on a second, Nick. Over there. Cool. Cool. Thanks, man. This is recorded online as well for the stuff that you missed earlier. All right. So, first thing, shh, not enough time. All right. That's going to be like my motto for this year. Not enough time. So one thing that's hard here is it says that the boom is negligible mass. So this means it's small enough it shouldn't have an impact on this particular situation. The question then asks, what is the tension in cable A? And what is the compression on the boom? So to help you out, I'm just going to tell you, you kind of want to draw the force diagram right here. Here. Let's look at the force diagram right there. What are the forces acting on that spot?
Gravity?
Not quite. Okay, so you're not wrong.
Force
You're not
bring
wrong.
down.
No, he's more right. Okay.
Oh.
You're not wrong with gravity, but I want to explain why that's technically the case. Okay, so what is actually pulling down on that location?
The ball.
No,
The string.
string. Meaning, if I hold this, a string in my hand, come on. I said string, not spring. I know, you get jealous, but come on, I got stuff to do.
That's funny.
All right. The force of gravity is on the mass. Yes?
Yeah.
Is it on my hand? No. What's pulling my hand down?
The string.
Tension, right?
Almost.
So this, you're not wrong. The string, it's tension. So technically, this is force tension. Now, I didn't have you draw a force diagram on this guy, but let's quickly to the side do that. What is the force diagram on that guy?
On which guy?
This little ball right here.
Ball.
Force tension.
That is force gravity
Force tension up.
and force tension up. What is true of those two forces?
They're
Could be
equal.
down.
Which law indicates that they're equal?
One.
First.
law.
Correct. Since it's not accelerating, they're equal. Now, how should this tension relate to that tension?
I do believe it should be the
They are equal. So that's what I mean, Grant, when I say you're not wrong by saying force gravity. It is 200, but it's not gravity that's actually on it.
Yeah.
Why are these two tensions equal?
Because they're using the same tension rope.
No, well, sort of. All right. These two are equal because of first law. These two are equal because of
Third law.
third. Correct. What is third law?
Everything has an equal opposite.
Every force
Yeah.
has an equal and opposite force. Now, what's a little bit confusing, especially in this example, is it's commented in the problem, and this is why it commented in the problem, that we're trying to find the tension in cable A, not cable B. So actually, the force that goes that way is
Spring.
tension.
Why do I say spring?
Don't know. So I'm going to do something that is technically wrong, but I think will help us as we continue on, even though it is actually tension. Yeah, I'm going to go back here and call it gravity. Now, if this was its force diagram, is there a force up and down in the line?
Yeah.
So it's possible to be balanced because there's a positive and a negative. In the X, is there currently a possibility of it being balanced?
Yes.
No. Because which direction is the force in the X here? Left. Is there anything currently pushing right?
No.
So what would push right here?
The
This rod would actually provide, and I think this is the one time we'll actually use this in this class, force compression. Compression is when you push in, an object pushes out. And if you struggle with that, that's why I got this set up here, okay? You'll notice I actually have it tied to a rope right down here so that it can move. And you'll notice that if I don't have it tied right here, which way is it definitely going to accelerate?
Negative.
That way. So it only stops accelerating that way when this stick pushes straight that way. If you don't believe me, you can come up to this example and you can provide the force that way for the stick by literally holding it just like this. Which way am I pushing this? This way. All right. Now the goal of this was to find force tension and force compression. But it doesn't feel like you have enough information, so let's walk through this real quick. Make sure we're off phones. Okay, so what force do you currently know?
Force of gravity.
Force of gravity. Cool beans. Given and find. Well, this is fine here. We've got the given in the picture. You are welcome to write the given in the picture as well. What are the only two givens? Even though they're up here, just tell me what they are.
30, 200.
We know that 200 newtons is the weight of that object, right? Force pulling down. And we know that what's the angle?
30.
30 degrees from the wall to the string.
Almost like
Another good way to say that, and you'll see why later, is to say that is 30 degrees with the vertical. Basically, with the up and down, it's 30 degrees. Regularly in here, there's only two angles that regularly matter, with the vertical and with the horizontal. Okay? The nice thing about saying with the vertical is this. If I've got two lines, and that's 30 degrees, guess what that is?
33.
That's alternate interior angle. Every angle with the vertical is 30 degrees here, regardless of how you check it. So, I've got my given and find. I've got my force diagram. What comes next? I feel like we should be a little faster on the pickup.
yeah, it's just beeps.
We've got Jeff done. Given and find are done. So, E.
Way.
Specifically,
Sigma.
sum the forces. And we got the Y and the X. Which one do you want to do?
Why?
Y.
What?
You could
Why
do it
first?
Agreed.
We know more.
All right, so here we go. Let's switch colors. This is not great over on the blue.
What is
Hey, go pink.
What is this whole question for here?
We haven't got there yet. I think we're not get there today because you guys keep interrupting me. We've got stuff to do. All right, I got like 2 more, this example and 2 more. All right, is it accelerating in the y? Sorry, that sounded a little bit bitter. I'm not bitter. I just want to make sure that you guys get a little bit more focused so we can get through content, because when we don't get through content, you guys get sad in the homework and like, I don't understand why we don't get this. Or maybe if we focus a little bit. Sorry, point is, moving on. All right, sum of forces in the y. Is it accelerating in the y? No, it's not. Is it accelerating in the y? No, it's not. What are the sum of forces in the y? See if you can't do that on your own in 30 seconds. Write that equation down. Write it down. It's not as easy as people usually try to make it. Is it acting in the y? Which direction is it in the y? Is it only in the y? All right, somebody tell me what sum of forces in the y should be.
It's gonna be your ft of y
Correct?
minus your
Correct. Why is FTY? Why is it FTY, not just FT?
FT, and it's only in y.
I showed this yesterday. I'll highlight it again. FTY is that right there. It's how much tension is pulling in the y. Or it might be even easier to see it here. That is FTY. This math is super simple. It just tells us, hey, FTY is equal to force gravity, and therefore they're both equal to
200.
which makes sense. Gravity's pulling down at 200. If it's not going anywhere, something better be pulling up at 200. Yes?
Yeah.
Except, is that FTY what we're looking for? Is that the tension? No. But if I take this guy right here and highlight what I just drew, here's force tension. Here's force tension in the y. And what's that angle?
30. Oh,
30 degrees. And anytime you're given an angle, you should probably know that the problem is going to ask you to do
trigonometry.
trigonometry. Correct. I'll just complete that little triangle right there. And what trig? Now, another thing real quick, make sure you're very careful with your trig and do not just go ahead and make assumptions of cosine is x and sine is y anymore. Let's just do the trig. What 2 sides do we have?
We have
Adjacent
and
So we should use
cosine.
cosine of 30 degrees is equal to force tension in the y over force tension. We're looking for force tension, so doing the algebra quickly so that I can get through this. Number 1, be careful here. So many people don't. There's 2 steps to this. Either 1, invert both of them and solve for FT, or personal preferences, get rid of the fraction first. Since I'm trying to get FT, I'm going to get it on top by multiplying both the left and right by FT. And then what should I do?
Then divide by cosine of the.
Bringing you some trig that you don't usually see. You don't usually divide by cosine, but that being said, the reason why that is because you usually have the hypotenuse and you're trying to get the sides. In this particular case, you have the side and you're trying to get the hypotenuse. What is FTY?
200
And so what's 200 divided by cosine of 30?
230.94.
Let's just go 230. You're fine. I would say 231 if I were in your shoes, but I know what's going to happen in a second. If you want to say 231, feel free. Next, that was force tension. That's the first answer. The next question is, what was force compression? Now, if you ever get stuck on one of these problems, there's a spot where you shouldn't get stuck. And it's this. If you don't know what to do, sum the forces in the x and y. So if you sum the forces in the y,
Yeah, that's sum the forces in the x.
more than likely, that's where your other answer is, summing the forces in the x. So here I go again, all on my own, down the only road I've ever known. All right, what's the acceleration in the x? 0. Cool.
Doesn't say, I don't think it is.
What are the sum of forces in the x?
0. Force compression.
Thank you. Positive force compression. And
Negative force tension on the x.
so, once again, this equation is kind of dumb because it says something that makes perfect sense. All this equation says is, well, it's the same as this equation, sort of. What does that equation say? Hey, everything up equals everything down. What does this one say? Everything left equals everything right. Of course, no, it's not. It's 100% true. Okay, that is correct. But do we currently know force tension in the x? But if you look at this little triangle right here, what easy thing could you do to get it? Well, let's be straight. I was just looking for trig because the answer is about 3 different things in trig. One, you're right, you could do Pythagorean theorem, not the easiest. The second thing that you could do is sine. Okay, why could I use sine? Because it's the opposite. The third thing that you could use is use tangent because it's the opposite. Okay, because you have everything else. So pick one. I don't care.
Sine.
Sine it is. So the sine of 30 degrees is equal to the opposite, force tension in the x, over the hypotenuse, force tension. In this particular case, unlike the last problem, I'm not trying to get ft, I'm trying to get ftx. So all I got to do is multiply ft on both sides. And we get 230 newtons times, anybody know what the sine of 30 is off the top of your head?
115.
Okay, what's the sine of 30 off the top of your head?
Oh, 0.5.
Half. Which means, yes, it's half of that. 115 newtons, which is why I didn't make it 231 earlier so that I could do that cleanly. Although, if I said 231, it would just be 115.5. You get it. Moving on. Questions, concerns? Okay, I got one more problem. This problem is going to be set up, and I want you to try to do it for Monday. It uses the stuff that we have been discussing and has to deal with a drone, or really, honestly, anything that kind of moves this. Now, if I have this drone actually on, I'm not going to turn it on for the sake of time right now. What is its force of diagram when it's hovering here? Gravity down.
Force.
So I'm going to draw a terrible drone.
Force thrust up.
Okay, force gravity down, and for your sake, the best option right now would probably be random, but in truth, it's actually called force lift. So I'll just say L for right now. Let's answer this. Okay? If this guy stays the exact same speed, meaning, sorry, if it stays the same speed in the blades, you don't hear it whirl up or whirl down, the engine pushes just as hard, and what does a drone do to move forward?
Tilts.
It tilts. If it does this, and it does not speed up its engines, this guy is going to definitely do 2 things. What are they? Okay, so the force diagram now looks like this. Force gravity here, and which way should lift go?
To the right.
Why does it, I heard the first thing and that's correct, why should it fall?
Because it's not pushing out as much.
Correct, because your hypotenuse stayed the same, so now there's less lift in the y, so is it balanced in the y anymore?
No. So
No.
it would need to speed
So
up.
if and most engines will do this, you can see it. When drones, and they usually have it programmed in, this one is, I don't actually have to do it. When it tilts forward, what should you hear the engines do so it stays at the same height? They will speed up, which technically does what to the force diagram?
Unbalanced.
Makes the lift.
The force lift should be bigger so that the hypotenuse is bigger, but yes, force lift in the y is the same. So here's your problem. Let's assume from the y it tilts forward an angle. What angle would you like?
15.
15 degrees. The weight of it, I'm going to tell you, is 5 newtons. Now notice I've told you the weight, not the mass. If you have the mass, how do you usually calculate weight?
Mass times gravity.
So just a heads up on this, not that it matters here. Actually, it does matter here. If you have the weight, can you always get mass out of that?
Yes.
Yes, they go back and forth with this exact same equation. If you have mass, multiply g to get force of gravity. If you have force of gravity, then to get mass, you divide by g. Just do the algebra here. Here's the thing. Let's assume that lift is increased so that it stays at the same height. But will this accelerate?
Yes.
Why? I agree with you, yes. Why? Given this picture, why will this definitely accelerate even if it's not accelerating in the y? There's only one force in the x. If there's only one force in the x, what does it got to do? It's got to accelerate. Correct. So here's the question I have for you. Using these 2 numbers, calculate its acceleration. And again, it's not losing height. I'm going to write this problem up and put it online. I would like all of you to try it for Monday. I'm going to look at your efforts, and you will get points for having tried. The only thing you have to do to get it is try. If you don't try, 0 points. If you try, all of the points. Please try this problem. Sorry, Tuesday. Bye bye.
Oh yeah, we did Monday off.
Happy Veterans Day.
The end.